So okay, wait. All right. I don't. Did I show off Reaxis? So Reaxis is amazing. Is I'm trying to understand how to I found this YouTube channel called Total Synthesis that is badass, man. He showed the Woodward lysergic acid synthesis, which we can probably find. And I'm not even interested in the lysergic acid thing, but what am I trying to do? Oh yeah, natural. Why doesn't this work? I don't get this. Okay, so they only have the Woodward lysergic acid synthesis, which is already pretty complicated, but I can understand most of this. This step I found really interesting is the hydrolysis of a nitrile to a carboxylic acid. And actually, wait, to an ester, methyl ester. Huh. And I don't know how the Rainy nickel thing works. I don't know, because Rainy nickel I thought was a reduction thing, but this is. So I don't really know about that. But what I'm trying to say is, if you look at, well, maybe I'll just pull up the video. Dude, also, these chemists are so funny. Linus Pauling is just like casually like tearing apart asbestos, and he's like, "This asbestos is really fluffy." Um, wait, this is not the right thing, bro. I'm just trying to pull up a. Dude, I'm gonna get on a freaking watch list. I don't even care about this. Wait, is this? This isn't even the right one. Yeah, this is the video that I want. So in 2011, Kyoto University did. Oh, also, dude, these old school chemists are insane. They said smoke a cigarette while you're using this hydrogen cyanide solvent. Because if there's a leak, you'll taste it in the cigarette. It's like, dude, these guys are nuts. Anyways, what I wanted to show was this one step where I was like, I mean, in general, he says it better than I could, because he's this guy seems like a real chemist. But like this step of forming these two rings at once, I mean, like, look at, like, first off, you have an allene here, and all I'm trying to say is like domino cyclization. That's cool. Is that we're getting more advanced and complicated in our understanding. And wait, but there's one specific part where he says that there's an unexpected step that happened. I think it's sort of towards here.
Sonogashira coupling was employed. The precursor vinyl bromide can be accessed from the aldehyde via olefination. You're confused and got your hopes shattered already. This last reaction might be one that you've already heard of. It's an electrophilic aromatic substitute, most that in both of oxyrate prime fashion. In addition to the desired product, both this isomeric exocyclic olefin and this ketone were isolated as side products. Can we rationalize their formation?
Yeah, so this is what I find cool is like I remember when I was an undergrad for the first time, and we were talking about self-driving telescopes um for astronomy. And it's like, how do you, at the time it was like, how do you use reinforcement learning to guide whatever, this objective function that, I mean, the objective function is basically always like, what do we not know? And like trying to rationalize the maximum amount of what we don't know. Now it's probably hard to predict like which un which unknowns that don't conform to the current understanding are the most will be the most impactful. I was watching the newest Three Blue and Brown Dwarkesh podcast, and they were talking about Galois theory and like how like it's very hard to know really which ideas are going to crystallize into something that's extremely valuable. Like, it took 100 years before group theory and Galois theory kind of became legit. And I don't know anything about Galois theory. I know maybe a tiny bit of group theory, but yeah, it's just interesting. So, but the question would be then, it's like, how do we? I mean, it's all about compression, right? So it's like, how do you take this corpus of all the chemical reactions that have ever been performed and just compress it, compress it into a way that we can. Well, I mean, maybe the question is even like, is it even valuable to compress it in a way that humans can understand it? Or is that like, because like, let's see if I can find this. I was talking to chat about scientific revolutions. And and I was talking about how like my feeling is that the real or an important way to frame the evolution of scientific discovery in the past 100 years is the transition from linear science to nonlinear science. I think that's a pretty good way because even deep learning was catalyzed by nonlinear functions. So anyways, let's see. I was trying to find this part here about yeah, so I mean, but there's also this trend that deep learning and AI um change the actual practice of inquiry. Instead of hand driving compact laws or explicit symbolic rules, scientists and engineers increasingly build systems that learn structure from high dimensional data. Right? So it's like, well, anyways, I mean, I feel like a lot of this is fruity, but there was or I'll just ask this thing. I think there's a Quanta article about it. I didn't even really understand what the hell this thing was talking about. But I want to read this paper. But I also want to know, like, I guess it's useful to know how people are doing it now. All right, anyway, I want to read this. I actually don't even care about the water thing that much. The advancement of machine learning and the availability of large-scale reaction datasets have accelerated the development of data-driven models for computer-aided synthesis planning in the past decade. Here we detail the newest version of AskUs, an open-source software suite for synthesis planning that makes available several research advances in a freely available practical tool. 4 one-step retrosynthesis models form the basis of both interactive planning and automatic planning modes. Retrosynthetic planning is complemented by other modules for feasibility assessment and pathway evaluation, including reaction condition recommendation, reaction outcome prediction, and auxiliary capabilities such as solubility prediction and quantum mechanical descriptor prediction. I don't know what that means. AskUs has assisted hundreds of medicinal, synthetic, and process chemists in their day-to-day tasks, complementing expert decision-making. It is our belief that CASP tools are an important part of modern chemistry research, and that they offer ever-increasing utility and accessibility. So I wonder if it's it's an interesting rule to think about that, like to always ask yourself, can AI just one-shot this? Like maybe that's delirium, right? I feel like that is actually a pretty good phrase because but also at the same time, like I think it's a good idea to build some good I mean, you do need if you okay, it would be a great idea to build a tool, or actually it's not even a tool, it's a benchmark. And it's like just like how we have Arc AGI and all of these, and Agent Bench and all of these benchmarks that evaluate the intelligence of AI agents. It would be useful to build a benchmark, and these guys might actually have the benchmark to see if AI can just kind of one-shot it. And I think there's probably, in a similar way to lean proofs and having AI math proofs and stuff like that, a feedback mechanism. So, but actually, I think I read something that the unit distance problem was solved not with because anyways, I think even Dwarkesh and Grant were talking about like how important is formalization, but I think maybe in chemistry, well, I think maybe I just have a bias towards formalization, but and maybe that's wrong. Yeah, right. So this didn't even use lean. Hold on, I gotta take a piss. But the thing that I'm trying to say is that you want tools that would give the AI an ability to inspect molecular graphs and stuff like that, because otherwise, I mean, like if you're providing it images of molecules, like drawn molecules, it's just there's got to be a name for that kind of AI failure mode, because it's like it's so common, and it's not something that you should use to justify, hey, the AI is dumb. It's something that basically says it's a context engineering problem. Basically, it's just like you provided the wrong information. Okay, so I actually want to go then to um much of AI progress these days is staked by performance on benchmarks, and coming up with new and novel benchmarks seems like an important role in the development of AI. Are there any? It seems to me that um, the biggest benchmarks that people care about right now are um, um, well, mostly software development. And uh, hold on. Anyways, I'm wondering, is there any benchmarks out there for chemistry total synthesis? Oh yeah, like SWE-bench. Yeah. Yeah. Okay, I gotta go. Okay. All right. So I need to go. Okay, wait. I gotta go.